right, my friends, welcome to section 3.3, part 2. This is about the product and quotient rules for derivatives. Okay, let's start you out with a little warm-up, just a little food for thought. So we're going to start off by talking about the product rule for derivatives. So I just want you to think about a statement here and figure out for yourself, do you think the statement is true or false? So here's the statement, ddx of, and so what I'm going to be putting you in the situation I'll put you into here is where you're taking the derivative of one function of x, so like 3x minus 1, times another function of x, 5x plus 2. And what I want you to think through is it okay to just take the derivative of the first function of x, so like ddx of 3x minus 1, and then multiply it by the derivative of the second function of x, so ddx of 5x plus 2. So is this equal sign telling the truth or not? So think it through on your own, decide what you think. And then your thinking process basically should be based on the order of operations. So let's look at the left side. Let's investigate the left side of the equation. So on the left side, you'd follow the order of operations, which would say do grouping symbols first. And so we'd work from the inside out. So on the left side, it has you doing ddx of 15x squared. I'm just expanding this out. Looks like, I think, plus x minus 2. And then if we finish the left side out, we would end up with, so now do the derivative. So we'd have 30x plus 1 if we took the derivative of this expression. So now let's do the right side. The right side has you doing the derivative first. So what's ddx of 3x minus 1? It's 3. And what's ddx of 5x plus 2? It's 5. So on the right side, we got 15. So while I'm sure there's an x value that would make 3x plus 1 equals 15, this statement certainly is not true for any x value. So I'm hoping that you were thinking the statement was false. And how come? Well, because when we distributed the derivative over multiplication, it basically changed the order of operations, and so it gave us a very different result. I suppose if you wanted to make the statement true, you could just say not equal to, and so now it's a true statement. Anyway, so the point is this, we need to have a little bit of a conversation about what is the product rule for derivatives. So even more important than knowing like what it would equal, let's talk about what it's for. And at this point, I hope you would guess what it's for. So the product rule for derivatives is for taking the derivative with respect to x of one function of x times another function of x. And at this point, I hope we at least know what it's not going to be, and don't bother writing this little part right here. Here, I'll use green pen. Don't write this part that I have in green pen. This is not going to be, and based on our warm-up here, I hope it makes sense. Sadly, the product rule for derivatives is not just ddx of f of x, also known as f prime, times ddx of g of x, also known as g prime. You know, sorry, that's not it. So let's see. So let's take this out because that is super not what it is. And if you were here, I'd ask you kind of what order you want to do things in today. But I think what I'll do is I'll go ahead and tell you what it is. You will not like it at first, but we'll talk about how to have a way to remember it. So ddx of f of x times g of x is, I think of it as 1d2 plus 2d1. So here's what I mean. It would be the first function times the derivative of the second function. So this 1d2, that's how I remember it. And then plus the second function times the derivative of the first function. 1d2 plus 2d1. So I'll just kind of put that underneath. The way I remember this is 1d2 plus 2d1. Kind of the d means derivative of in my mind. Okay? All right, so that is the product rule for derivatives. We will prove it. So for anybody who's totally into proofs, for the, let's see, we've got 30 people in this class. Let's see, for the 3 of you who are super into proofs, we will prove this in a little bit. But let's give everybody a second to like digest what on earth this mess is saying. So let's redo the warm-up using this rule so you can see what it looks like when you use it. So let's say you're doing ddx of 3x minus 1 times 5x plus 2. And just for the record, just multiplying it out and doing the derivative the way we did over here on the left side, that is actually probably the most efficient way to do it. But let's say you're trying to practice using the quotient rule, or sorry, the product rule. We would do 1d2 plus 2d1. So what does that mean? 1 in my mind means the first function as is, untouched. d2 means multiply it by the derivative of the second function, which would be 5. Plus means plus. 2 is 5x plus 2. d1 would be derivative of the first function, which is 3. So now if we were to then distribute the 5 in, we'd get 15x minus 5. And then plus, let's multiply the 3 in. So we'd have 15x plus 6. Combine like terms, you'd have 30x plus 1, which notice does match what we got when we just expanded it out and used more basic rules. Now that's not exactly a proof. Just because it works for one example doesn't mean it works for all. So we will show the proof. This is probably going to be the most interesting proof that we do. One of the more interesting proofs that we do in this little unit. So let's get started on that. So a proof of the product rule. So I'm going to start with, this is kind of a verify the identity style proof that you've seen me do in the past. So I'm going to start with a prompt of ddx of f of x times g of x. And we are going to fall back on the definition of derivative where this is your function you're taking the derivative of. And our goal is to show that it ends up being this adorable. So using the definition of derivative, we would say this is equal to the limit as h approaches 0 of f of the quantity x plus h times g of the quantity x plus h minus f of x times g of x all over h. So that would be step 1. Just go ahead and use the definition of derivative and this is your function that you're taking the derivative of. So this function with x plus h substituted in, subtract the function as is, and then divide it all by h. Okay. The next step, and I usually like it's kind of seems silly, but the next step is for me to, in a way, kind of like expand this in a kind of put like a big amount of space in between the terms. So it's going to look like this. It's the least fancy thing you've seen all day. So I'm going to take f of x plus h and g of x plus h. I'm going to leave a very strange and ominous gap, and then I'm going to write minus f of x times g of x way over here. Look, I expanded it. Okay. Anyway, all over h. Okay, so and as long as you can look at this and you can be like, okay, well, I don't know what you're up to, but at least that equal sign is still telling the truth, then you're good. So if you don't know what I'm up to, that's okay. So now what I'm going to do with green pen is show you kind of a fun little trick. What I'm going to do with this ominous gap here is I'm going to add a creative version of 0. And the creative version of 0 that is going to help us get somewhere looks a little bit like a train wreck, but it's minus g of the quantity x plus h times f of x plus, and I'd have to add this term back on, so that way I'm basically adding 0. So plus g of x plus h times f of x. All right, now if you're feeling anxiety right now because you're like, I wouldn't have thought of that. Well, me either. A long time ago, I looked this up in a textbook and I just kind of remember it after that. So thank you to whoever did think of that. And then I just keep using it. Okay, so as long as by the end you can see where we're going, then you are in super good shape. All right, my friends, the next thing that we are going to do is give this kind of a creative regrouping. So we're going to bring down the limit as h goes to 0. Don't forget that guy. And then we're going to split this monster fraction into 2 smaller monster fractions. So go ahead and use that bracket to group it all together. And so what you're going to see me do is group these 2 together. And then you're going to see me group these 2 together. Okay, I now realize that these 2 colors of pen look a lot alike. But anyway, okay, so we're gonna write this like this. So f of the quantity x plus h times g of the quantity x plus h minus, I need to learn how to write smaller, g of the quantity x plus h times f of x. And then that would have to be added to g of the quantity x plus h f of x minus f of x times g of x. And then it's all over h. And then if I put this one over h as well, then I hope it makes sense. These 2 would add up and be what you used to have. And my equal sign is telling the truth. Okay, so sorry for my horrible spacing. Okay, next we're going to talk about common factors. So if you look, and if you've been tortured sufficiently with factoring, then you should be able to look at the top and notice a common factor that we could factor out front. So then we would have the limit as h goes to 0 of, and the common factor for this part would be g of the quantity x plus h. So we would have, I'm going to write it out like this. And then what would we multiply that by to get this mess back? It would be f of the quantity x plus h minus f of x over h. I'm going to go ahead and distribute the limit over addition. So I'm going to have plus the limit as h goes to 0. And then on this one, I'm going to factor out the common factor of f of x. And then you would have to multiply it by g of the quantity x plus h minus g of x over h. All right, and if you are starting to look at this and feel like you know what we're up to, then congratulations. That means you have definitely been sufficiently tortured by the definition of derivative. But we're going to use one more property of limits. Limits actually do distribute over multiplication, something we've talked about back in chapter 11. Derivatives don't, but limits do. So in the next step, I'm going to rewrite this as the limit as h goes to 0 of g of the quantity x plus h times the limit as h goes to 0 of this mess, f of the quantity x plus h minus f of x all over h. Plus, I'm going to distribute this limit over multiplication here as well. Limit as h goes to 0 of f of x times the limit as h goes to 0 of g of the quantity x plus h minus g of x all over h. Okay, so now let's look at what we have. Let's consider each limit one at a time. So for this first limit expression, if you let h go to 0, what would this say? It would just say g of x. For this expression, if you let h go to 0 on this expression, then I hope you've noticed that this is the definition of f prime. Now let's look at this one. Let h go to 0 of f of x. Well, there's no h there, so you would just have f of x. And this one, let h go to 0 on this expression, and if you look closely, that is the definition of g prime of x. All right. Last step is just to point out the fact that addition is commutative, and so you could rewrite this with this term first. So f of x times g prime of x plus, and then g of x times f prime of x. And then we would bring our prompt down. The whole time we were finding d dx of f of x times g of x. And we found that it is indeed equal to your first function, untouched, multiplied by the derivative of the second, plus the second function times the derivative of the first, also known as 1d2 plus 2d1. Proved. There we go. All right, my friends. So that's the product rule. There is also a quotient rule. So the quotient rule, first thing I'd want you to think about is what would it be for? I'm hoping you're okay with it would be for d dx of one function of x getting divided by a second function of x. And I hope you can guess what it is. Sadly not, since division is pretty much just multiplication in disguise. Since the derivative did not distribute over multiplication, it will also not distribute over division. So just take a moment of sadness to mourn the loss of this rule not being that this equals f prime of x over g prime of x. And so let's talk about what it is. I'm going to write it down in its true form, and then I'm going to give you a very dorky way to remember it. It will make you very good at the quotient rule. It will also make you always hate me because you will probably never be able to do the quotient rule without thinking of this dorky thing. Anyway, so I will I will be stuck in your mind forever, and I'm not even sorry. All right, so here we go. So d dx of f of x over g of x is equal to your denominator, as is, multiplied by the derivative of the numerator, minus your numerator, as is, multiplied by the derivative of the denominator, all divided by the denominator squared. All right, try not to freak out. So the dorky way of remembering this is, and I'm going to point to the location on the left. So low d high minus high d low, all over the bottom squared we go. And if that is not enough fun for you for one day, then try out with a Swedish accent, or your best shot at a Swedish accent. A little pre-warning, I may have learned my Swedish accent from the Swedish chef on the Muppets. So here we go. Low d high minus high d low, all over the bottom squared we go. I'm so sorry if you're Swedish or you know someone who's Swedish and I just offended you with that. All right, so here we go. To remember this one, you can remember low d high, and then minus high d low, and that is all over the bottom squared we go. There we go. All right, one more time with the horrible Swedish accent. Low d high minus high d low, all over the bottom squared we go. So glad you're here today. Not really here. All right, anyway, so you should memorize that. With or without the Swedish accent, my friends, you've got to be able to employ the quotient rule. All right, the proof of the quotient rule is very, very similar to the proof of the product rule. And so for time purposes, I think we're going to skip to the part where we just practice using it, okay? We're gonna do one example, and then you should be pretty well ready for your homework, okay? example, okay, I think we're on example 8. I'm not totally sure. All right, you can change the numbering if you need to. So the directions for example 8 are for you to differentiate. Let's say I give you, for part A, I give you y is equal to 5x minus 1 over x minus 3. All right, my friends. So up to you. Go ahead and pause the video and see how you do it on your own, and then you can compare our work. I'm going to go ahead and go through it, assuming that you've done that. So we're going to take d dx of both sides. On the left, we would call it dy dx. Remember, if they call it y, you need to use Leibniz notation. On the right side, we would do low, which is just your denominator, d high, derivative of your numerator, minus high, d low, all over the bottom, squared we go. All right, from there, dy dx would be, let's just go ahead and simplify it a little bit, 5x minus 15. I'm going to multiply the negative and the 1 in at the same time, so I'd end up with minus 5x plus 1. I don't think squaring that out is worth our time, so I'm going to leave that factored. Let's see what happens when we combine like terms in the numerator. We'd end up with, so 5x minus 5x, so those vanish. And so it looks like we'd end up with negative 14 over x minus 3 squared. There we go. All right. And that's it. That's how you use the quotient rule. Now for part B, let's say I gave you y equals 5x minus 1 over 7. So think about how you'd go about this problem. So I'm hoping that you pause the video if you need some more time to think about it. There are 2 ways to do this one. There's use the quotient rule, or you could actually do it without the quotient rule. And what I would really like for you guys to exercise is kind of a critical eye, where you look at a problem and you ask yourself, do I have more than one way to do this problem, and what's the path of least resistance? Because in calculus, you're not going to want to take the time to do things the hard way every time. So I will show how to do this one using the quotient rule. It will work, and then we're going to talk about an easier way to do it. So with quotient rule, you would get dy dx equals low, which is 7, d high, which is 5, minus high, which is the quantity 5x minus 1, d low, remember the derivative of a constant is 0, all over the bottom squared we go. So you'd have dy dx would then equal, looks like I have 7 times 5 over 7 times 7. The 7's cancel, and you'd be left with 5/7. Okay, now let's talk about, for this one, let's practice the art of algebra before calculus. Because this is one of those problems where you actually had a much simpler way to go about it. So if you were to do this problem with algebra, since you're dividing a polynomial by a monomial, you could actually just distribute the division in. And I want you to notice that that wasn't so much an option over here on the left side. So, so if you rewrote the rule, you could rewrite it as 5/7 x minus 1/7. And then here you have a linear function, and remember a line graph is its own tangent line. So the slope of the tangent line at any x value would always just be that 5/7 value. So notice that both methods give you the right answer, 5/7, but do try to look at problems with a little bit of a critical eye before you start them. When I give you a problem set, there will be many problems where you could use the quotient rule or the product rule, or you could kind of go around it and have a simpler method. Always kind of look for those opportunities and ask yourself, is it worth the trade-off to do the algebra before calculus, Or is it easier to go ahead and just use, in this case, the quotient rule? And sometimes the answer is going to be it's easier to do the algebra first and use basic rules. And sometimes the answer is going to be no, you should just go ahead and use quotient rule or product rule. And sometimes it just comes down to a personal choice. All right, my friends, I hope this makes sense, and we'll see you in the next video. Take care, everybody.